Okay, guys, we're going to continue with our discussion. So this is part 2 of the video of just building the model for linear regression. So I'm going to share the screen. Right. So we should be here now. And so we're just going to continue. Okay, so let's go back to the script. So for those of you having trouble with that Firefox thing, I sent another email. Sorry with the error that you got. Hopefully they'll let us know. That, I have no, that's in West Lafayette, so I don't know. All right. So let's now, just to kind of review where we were, let's take a look at the script. So you can see we're building a basic learning template for a linear function or linear regression. For libraries, we have our data for temperature, Celsius and Fahrenheit. So, once we finish this, go home, play with it, predict some temperatures, and convince yourself that it does work, right? So we split the data. We did this, which is really useful, splitting the data, normalizing the data, visualize the data. And then now we have these 3 functions that we need to define: the model, the loss function, and the training loop, right? So always kind of they will be the main template, as I said, that we need to define whenever we're doing machine learning. So we call the functions, we call everything here. So we define the parameters, we define the learning rate, we define the optimizer, which in this case, as I've told you, is going to be called something called stochastic gradient descent, which is pretty complex. All right, so this involves getting a function, getting the second derivative of the function, using something called a chain rule. There's a lot going on down there. Okay, so there's derivatives. There's literally calculus in here, in this, the optimizer. But the beauty of PyTorch is that we don't have to worry about the calculus. They do it for us. Some people have gone to a lot of trouble to build these functions, figured out how to move back and forth, do their derivatives, calculate, the tangent to the curves, figure out how to update and everything for us. You see, although you saw me as just writing one single line of code, this is actually what does all the heavy lifting. Okay, this is the powerful thing that PyTorch is providing, the thing that that makes this very powerful. Okay, so we'll talk a little bit about that later, as I said in the lectures. But right now, I really want to get us to understand this. So we talked about the optimizer, and then we have here the training loop is in here, where we define everything basically. Right, this is going to be our main for loop, where we load the data and we do everything that we want. So now we need to define these, right? So let's look at, now training loop is going to be calling these functions, model and loss function. Okay, it's going to be calling them. So as you can see let's start with something simple. The model function, actually, if you notice, is nothing more than y = mx plus b, right? In our case, because it's a linear regression. So let's actually now, instead of informally writing it, let's actually define it a little bit more formally. So the beauty of PyTorch and TensorFlow and these libraries is that you can sometimes get into the actual math of things. Like you can literally write out equations and that's actually very useful, because sometimes you need to tweak, you need to tweak your models in some way or another, right? That's what you do basically. And so, people that do research, et cetera, they don't just use the built-in functions that are provided, but they use them plus some modifications, because they're experimenting with new ideas, right? The new ideas are what, might, in the stock market, right, give them an advantage to make more money, for us. So then let's think about the model. So the model is the prediction here. And if you remember, for temperature, that we're doing is TC equals W. We had already defined this before, but we're now going to define it here in the context of the model function. So it's going to be TCW times TU plus B. Okay. All right, so that's basically our function. So now we go in here. All right, and it's going to be 1, 2, 3, 4. Okay. And so now we're going to specify that same equation inside the function in a more formal way. So we're going to return basically the result of the function. The function will be what? It's going to be W times TU, right? And I actually like to write things like this. TU plus B. So TU is the input, right? The X, and then TC is the output, the predicted value. You can see that here, right? Now, so you might ask yourself, so where are these parameters coming from? Well, they're actually, TU is going to be passed as an argument, and we're also going to pass W comma B. Now this W comma B, remember, is in params. So do you remember params is actually what is going to get passed as W and B. Okay, guys? What I mean is this params down here. So this is params. If you notice, it's got these two. It's initialized with these two variables in the tensor, and so that gets passed on here. All right, and then the function basically. So what's happening is that W and that B, every time you're training, you're updating it, right? You're updating it based on the stochastic gradient descent algorithm, and then you're trying it out. Every time that you want to predict something with the model, you say, okay, I'm going to grab those params, whatever they are right now. I'm going to give it a TU. I'm going to predict a TC. That's it. And then you do it again, and then you do it again. But every time also you're training those params, hopefully eventually those params are going to be pretty good that you can actually predict really well with really good what is called with really good accuracy. You guys see that? All right. So this function I think is pretty straightforward. Now the loss function. Now this one might be a little bit more tricky. So what do we do in the loss function, right? So the loss function is, let's do 1, 2, 3, 4. So what is the loss function for linear regression? How do you learn? Huh? Yeah. In the loss function, what we're trying to do is we're trying to determine how good our prediction is. We have the real data, right? This is a supervised problem. So we have, for a given Fahrenheit to Celsius, we have it, right? We have, so then what we're trying to do in the loss function is we're trying to say, my model, this equation up here, which currently has a W and a B, right? Currently has a W and a B, can predict. And here's the value. Now compare that value to the real value. If it's exact match, then it's a good prediction. If it's a wide match, is a bad prediction. You see that? That's what the loss function does. Exactly that and nothing else. That is actually captured by a famous equation called the least squared error function. Do you guys remember that one? Least squares, LSC, from your linear regression class. So LSC is a function basically. And what it does is it's going to compare all the samples, right? Take the difference of them, square it, and then sum it. And by doing that, you kind of end up knowing if it does well or not. So let me grab my All right. So let me share, I guess. All right, so we're on the whiteboard, right? So as I said, there is the, so you saw the template. Just memorize this, if you will, right? Until it clicks in your head, just memorize. Whenever you're doing a machine learning model, right? 3 functions are going to be minimal, right? So one is model, right? That's the function. And the reason why we always start with linear regression is intuitive. It's very intuitive. And so therefore, it allows you to always memorize that and then build from that, okay? So you got the model function, which is y, w, x plus b, right? In its simplest form. Then you have the loss function, loss fn or just loss, and then you have obviously the training loop, right? So the train loop where basically the main for loop is located. Okay, so what's going to happen here is loss function is the one that I'm talking about. So this is for a line, for a linear regression. For other things, you know, other classification of cats and dogs, etc., this of course will be modified, right? And this will become, instead of this function, the architecture for a deep neural net. Okay, but we will start to see this next Monday, that, you know, when we start building on top of this idea, this new idea of neural nets. Now the loss function is actually referred, so if you think this is y hat, right? Y hat just means the predicted value. So therefore there is a real y, right? So then what you do is the LSC, or the least squared errors function, is a classic function. Just memorize it, you know, like put it in your, get a poster of it, you know, something, because these are the fundamental blocks of machine learning, okay? Even though the ones that we're going to be using later on are much more complex or different, still the idea comes from this, you know, from this. So LSC, basically the equation is what? Y minus y hat. What is that? All I'm doing is I'm taking for a given, let's take this example of temperature. For a given Fahrenheit, I've got the real Celsius, right? Because you can work that out. It's just, you know, chemistry or whatever. So I've got for a given Fahrenheit, I have the real Celsius. But I also have the predicted Celsius given my model. So the real Celsius is going to be this one, right? The y. The predicted one is going to be that one, the y hat. Therefore, you take the difference. Do you see that? Now we usually here either take we usually take either one of two things. You either do square or you do absolute value. Either one is fine, right? So the whole point is to get rid of the symbol, right? So to get rid of the symbol, because some values, because all you care about is really the difference, right? Not so much about whether it's negative or positive. So it's like you just want to get what's the difference between them. And so what you do is you do this, right? And then you're going to do this for all samples. You see that? So that means you're going to have y1, y2, y3. These are, and you're going to sum them. And then ... yn. Does this make sense? So all the samples that you have in your test model, let's say, or your train model, right? You have the real Celsius given the Fahrenheit, and you have the predicted one. Remember that you plug in that same predicted one into the model, it predicts something. And so now you add all of these together, and what do you want? Usually, you want the model where these are the smallest, right? Wouldn't it be great if all of these were 0, right? If all of these were 0, what does that mean? it means that this y is the same as this y, which basically means that this is the real and this is the predicted. So your predicted is very good. Let me put this in a context that you would really appreciate. Let's say it's the stock market, right? And you can figure out when to buy stocks. Well, that's more money for you, right? So the more precise it is, the better. So you would want these to be 0. Do you see that, guys? So there, what you do then here is that you're looking at, this is usually generalized like this. Like that. It's just a sum of all of those from I, to 0 to n, whatever. You see that? And you want to do what? The objective of the loss function, which is an optimization parameter, is to minimize that loss of squared errors. You guys see that? That's it. All right. So if we think about the function itself, right? So we have the real values in there, right? So you're going to look at the real and the predicted. See, these are the differences. So for this x here, the real is this one, right? That's the real one. But the predicted will be that, because it's got to be a straight line. You see that? If I have another x over here, think about it. This is the real one for that, but the predicted one is obviously the one on the line itself. You see that? So what is that difference? That little chunk. That little chunk. All of these little chunks you add. And you're going to pick the set of weights that gives you the smallest sum overall of those differences. So for instance, I'll give you this other example. Let's say that I have another line and it's here. Which one is better? Well, if you look for x1, the real x1 is there, right? But the predicted is here. Notice that the difference here is much bigger than this difference. You see that intuitively? So that means that obviously this is a bad line, this is a good line. That's optimization for you. That's how you do it. You can always do it randomly. If we had quantum computers, we could probably just do all of it all at once, right? But because our computers are not quantum computers, we need to have efficient algorithms to figure these things out in a fast way. And that's why we have all these things. Is this clear? Are there any questions? So a lot of what we're going to be doing is this idea, right? In the future, it'll be, something a little bit different. So for classification next week, since I have this kind of here, I'll just make the point that in the future, like next week, we're going to have pictures of shopping things, I think. It's like things from a store or something. So, but anyway, we're going to have items. Our goal will no longer be to fit a line through these, right? Because it doesn't really make sense. We still want a line, but it'll be a line now that does that. You see that? Now the line could be here, could be like that. If this is, line 1, line 2, line 3, line 4, which one of these is the best line? 3. Why? More accurately, right? Put in terms of optimization, it minimizes the number of errors or misclassifications. You see, for instance, this is a headache right here. You have 1, 2 misclassifications, right? This line over here, you have 1 misclassification. This line over here, you have many misclassifications, right? You have 4. This one has 0 misclassification. Do you see that? So that's going to be the goal. We use maybe a different function for that instead of LSC, but it's the same thing that we're trying to achieve. Does this make sense? All right, good. So now hopefully that kind of helps out to better understand this, what we're doing. So let's now go back to the code so we can finish it up. So now hopefully more intuitively you understand. Let me just disconnect this. Hopefully now more intuitively you understand what I'm about to write. So that function that I defined, the LSC, you can see it can be written out actually. Now this will probably be the only time when I do this. Okay, when I actually write out an equation for LSC like this, I always like to do it because it's basically, as I said, it's basically this one, right? So this function that I wrote over here, this one, this is the function for LSC. I'm gonna write it out kind of like this in the code, but going forward, we don't have to do that because that's what PyTorch is for. Every one of those functions, every one of those equations for losses just has a function. So we can just make a function call with some parameters that'll take care of it all. However, you do have the flexibility that you can modify it if you want to. Like if you're doing some advancements or have some insights. So let's go ahead now and write out the equation here. So it's going to be squared diffs. So squared diffs, and that's going to be equal, as you probably can see, it's going to be the TP. What is TP? TP is going to be the predicted. That's why it changed from TC or TU to T underscore P, is the predicted value from the model using the parameters and the input. And so TP minus TC. What is TC? If you remember, TC is the values that we already had. Okay, the real values for Celsius, for instance. All right, so we just take these parameters and we're going to raise this to the 2, so the square. Also, we could have used the square function. There's a lot of ways of doing this. But this is actually, now keep in mind, we only add this line. We don't have to do like a for loop, or we don't have to do like all of them because this is a tensor, right? So one thing that may not be so intuitive to you guys right now is that remember that TP, TC actually have a lot of values in them, right? They're vectors, right? So basically so that TP, when we do that operation, there will be, let's say, 7 predictions, and TC had the 7 real values. So we do the whole operation as a vector, and we have the differences then as a vector as well. Do you guys see that? Is that clear? All right, since I have a vector of squared divs here of, let's say, 7, now all I have to do is sum basically, or calculate the mean of it, and that's it. Right, so it's entirely, it doesn't really matter if it's the mean or you can sum it. It's just, either one should work. So then we return squared diffs dot mean. Okay, or sum, either one. Play with it. Look at the differences between mean and sum. That should be fine. All right. So this will return basically, as I said, the sum of, let's say, the sum of all the values. Your goal will be for that to be minimized as much as possible. Okay. Questions? All right, good. So it sounds like it's making sense. So at this point, we've defined the function and the loss function. Okay, both of them have been defined. And now what we're going to do is we're going to just call it the training loop. Remember that the training loop is actually somewhat the more complex. Huh? Oh, that the parameters, right? Yes, I knew I was forgetting something. And the parameters will be exactly as you said. So the TP is the predicted value. We still haven't defined that one. So that one needs to be in the main loop. And then the TC, of course, is the other one. Yes, good catch. All right, good. So now that we have this, we can go to the train loop. Remember, the train loop does have a lot of parameters. Okay, so it's going to take n epochs. And epochs, it's going to take the optimizer. It's going to take the params. It takes train TU. Val TU. Takes train TC. And val TC. Okay, so these are so then 1, 2, 3, 4. So now the first one is we're going to repeat everything n epochs, right? So we do 4 epoch in range from let's say 1 to n epochs. Okay, so that just means we're going to repeat all of this 3,000 times. Okay, then we do 1, 2, 3, 4. Right, and now we need to specify the order. And basically at the end also of train loop, you might, let's just, before I forget, let's add the what we return as well. So in this case, it can be anything really. A lot of people just return the parameters, the params. Because the idea being that once the training loop is finished with its execution, the output really is those parameters. And I can't stress how useful it is to have the params in this variable like this, in this format. Think about it. You're building the model, right? You're building the model with some architecture, but you have all the weights in that thing. And then you can move it around. You can study it on your own. You can actually try to visualize it in some way and all kinds of things. That's very useful. It used to be that you couldn't do this, like with the TensorFlow 1, you know, it was really not designed for that. And now this is very, very useful. All right, so anyway, so let's go back to the for loop here. So in the for loop now, we have 4 sections, if you will. All right, so let's think of it that way. We have 4 sections in it. Oh, and sorry, guys, I did receive a reply about that Firefox thing. I think it's unlock-Firefox, one word. So that we were putting a space. Some of you tried it like that and it worked. It doesn't work either. Yeah, all right, so you guys knew the answer all along. All right, so it's gotta be like this, just sorry. For those of you that were having this problem, I think you, right? It's actually like this. No space. It works now. It didn't occur to any of us to try. All right, anyway, it works, great. So I'm glad you guys solved it. All right, perfect. So sorry about that interruption. Let's go back to the script. So as I was saying, we were defining the loop. So we're in the epoch, and this is really divided into 4 sections, okay? So the 4 sections are really to call model and loss, right, for the train data. Then we call model and loss for the validation data. Then after that, we call the optimizer. We do backwards propagation and take a step on the optimizer. It used to be that you didn't have to do all this, but PyTorch does it this way to give you even more flexibility, okay? That's basically what it is. They give you a little bit more control of everything that's going on. Okay, so let's take a look at how that works. And I'm going to write this out actually. We'll remember what I said. Whenever we're creating this, we're putting the data in tensors, and then we're also defining functions. So we end up creating what is called a computational graph, okay? And this computational graph, imagine it's just like a tree or something with nodes and links. Some are tensors with data, some are function operations, etc., that you're performing efficiently on these tensors. However, you can actually create multiple computational graphs, not just one for this, right? There could be multiple computational graphs. So I think actually PyTorch does it that way by default. It just wants, it separates out things. So for instance here, this one is a separate train computational graph. Okay. And then over here for the training, and then we're going to have, just make sure the indentation is correct. This one is a separate, other, let's say, val computational. Okay, so there's basically two. So, and the only thing that these graphs will have in common really is the weights. So that's the beauty of this. It's like you move around the weights, right? That's why you have them controlled in one single variable. You can move them around from one to the other. So here, for instance, we do the one for training. And we're just going to say train TP. Remember, I usually sometimes like to use pred, is just a little bit more specific, but P stands for that. So what do we do here? We call, so this is the first one, the main training one, where we call the model function. So this one above. We're calling this function up here model. And what do we provide here? We need to provide, obviously, that takes TU, right? But it's going to be a train TU. You guys see that? Train TU? Yeah. And then remember what I said, it had W and B, right? W and B. So what we can do to pass the parameters is just use asterisk params. And that will basically, as long as they're in the same order, it'll pass the parameters into those variables themselves. Got it? Just kind of writing into memory, if you will. Is this part clear? All right, sounds like it is. So model, what is the function of model? Model takes whatever the params are, whatever TU is, calculates an output, right? Predicts Y, and it returns it. So therefore, train TP is the predicted value, okay? The predicted value given the training sample. Once we have the predicted value, what do? We call train loss. We call train loss, and that's going to be our loss function. Loss Fn, the one above here, the one that I just explained a second ago. A loss Fn. And what does this one take? This one will take TP and TC. So the predicted values here, train TP, right? Because we're going to compare them. So train TP. You guys see that? That's the predicted vector. And then we also feed the real vector, right? The real value. So that's going to be train TC. Is this part clear, guys? It's very important you understand this. All right. So now that we have that, that's basically it. And that's the training of at least predicting the values. However, so in this iteration, remember, in this iteration, we take the parameters, we predicted some values, we calculate the loss, work that out in there. And then we still need to do the gradient descent part. Okay, so the gradient descent, but the gradient descent, remember, is already tied to the parameters. Okay, and so now here we do the next part. This is going to be for the validation. Now, because this is the validation, we basically are going to turn off the gradient, which means this data is not going to be used to train. It's only for validation, right? To do that, one way of doing it is to say with torch dot no grad, no gradient, right? So that kind of implies that we're going to do this part, but it doesn't update the weights. 1, 2, 3, 4. And we're going to say val, again, we repeat the same thing, TP, this time equal model. So model, and this will take val TU, comma, and it's going to take params again. Okay. And what with the predicted value, we're going to calculate the loss. So we're going to do val loss. So we're going to do val loss FN val TP, which is the predicted one here, right? The predicted val TP, and then val TC. Okay, and then you can always do an assertion, just to double check. So you can say assert, so it doesn't update the weights, that val loss dot requires grad equals to false. All right. So again, this is just so that we can do validation, but without updating the weights. What does that mean? Opening a video. All right. So now that we've done this part, okay. The only tensors, these two so notice that there are two computational graphs here, the training one and the validation one. But the only tensors these two computational graphs, train and val, have in common is the parameters, params. Okay. Otherwise, they're different, right? They're very simple, but you know that's what they are. Now, this part here, this is something that I find very like a little bit strange. But this is something you have to do with PyTorch. So this is almost like a utilitarian thing you have to do. And again, it's just that PyTorch gives you so much information, right? That sometimes you have to like turn off certain things. So in this case, you have to say here, around here, optimizer 0 grad. 0 grad. And the explanation that I found for this is that basically this is cumulative. This optimizer is cumulative. That means it kind of keeps all the updates together. So in case you want to see them. However, every iteration that you're doing this, you actually want these values to be blank. Do you see that? So all you're doing is you're blanking it out so that when you make the updates to the weights, it's actually just for this iteration and not an accumulative thing. Does that make sense? So that's why if you notice, what this is saying is optimizer basically 0 out the gradient, okay, of the optimizer. And this is just something, as I have found, you just have in there, which to me is very different from like TensorFlow. You didn't have this before. But you know, that's basically, as I said, because you may, for some reason, want to look at the cumulative effect, right? And so at some point, let's say at iteration 1500 or 1,000,000, you want to see something like that, but otherwise you just zero it out. All right, so it would just be there. So now that we've done this, okay, now we're going to say that we need to do two things. We need the optimizer to do it, to do train, to do updates, but we also need to tell which loss needs to be back propagated. Okay, which loss needs to be back propagated? Because remember, all we've done, if you notice, is we've gone forward. We haven't gone backwards. You guys see that? So it's almost like, look at model. We give it the value, the params, it predicts something, right? Then it compares it in that other function and it gives you a value, right? Once it gave you that value, you're about to now update things, right? So you're about to update things. So you're going to say basically back propagate and then take a step in the optimizer, okay? And that's what we do. And as I said, remember that the idea there is this. Let me go back to the whiteboard. Kind of explain that. So it's a little bit more intuitive. So imagine I'm going to use a more complex model for this. But let's say that we have something like this. Currently, the data that we have really just looks like this. So it's not very interesting, to be honest, right? That's all it looks like. The architecture. But let's say that we have something in the future that looks like this, like that, right? So what happens is model, right? In model, you give it these inputs. That's the X, right? The Fahrenheit. It's going to go through this network in that direction. That is the forward pass. And it's going to predict some output. One of these is the output, right? Then you also have, so this is the Y hat, the predicted. But you also have the Y real, right? Therefore, in our example, we do Y minus Y hat square and all that, right? That's that loss part. But then we still haven't done anything to the weights. You see that? The weights are still just sitting there, right? We use them to go forward to predict, but now we need to do what? We need to update them. You guys see that? To update them, we need to take the result of this, right, of this comparison and go back like that. Does this make sense? So that we can actually then modify these weights. Okay, they need to be modified. The values of these links are the weights. They need to be updated. That is referred to as the back propagation, right? And so we do that with the optimizer. Do you guys see that? So we need to kind of tell the algorithm, okay, modify going back now, you know, by taking a step. All right, so that's really done by doing the following. And now we go back to the script. And here we're going to say train loss. Now notice we only do this for train because we also have val loss, right? But we're not doing it for val loss. So we only do it for train loss. And we're going to say dot backward. We have in PyTorch, we literally have to say it that I want you to do it in reverse. So, and that's only done, the back propagation is only done for the train loss. And so once we, so this is like specifying a parameter that we're going to work our way back. And then, and the last step is here to say, okay, optimizer dot step. And now it actually does. This is the moment when all the weights get updated, okay, in this iteration. Is this clear, guys? And that's it. At this time, all the weights are updated, and we can we would finish and then go back to next iteration or next epoch and so on. Okay, so that's it. That this is usually the main structure. The last part here is just like a print statement. So we can have some print statements here, just kind of visualize what's going on. So for instance, let's say if epoch less than or equal to 3, so that we only see at the beginning, right? Or epoch modulus 500, right, equals 0. This basically is a trick so that we only print every 500. So at 500th iteration, we print, right? So I do colon there. And now, so now I'm going to print out the loss of both train and validation, just to see how my model is kind of working. Okay. So I'm going to do here 1, 2, 3, 4. And I'm going to say print. What am I going to print? So I'm going to print F. So epoch format string here, epoch. And then this is for the training. We're going to say training loss is going to be train loss. So train, oops, train loss. So this train loss, right, is capturing the information about how the losses are doing, right? You guys understand that? What are we trying to do? We're trying to minimize those losses, right? The better our model, the lower those losses should be. You guys understand that, right? So the sum of errors should be smaller. But we want to visualize that by printing it out every iteration. So I'm going to do train loss. But let me finish this one, because this is an object, so we have to say item, just like that. And then we specify, because this is a format string, the precision, so dot for float, basically. Okay, that just prints it out a little bit. Let's add a comma here. And then let's finish this one down here. So let's say now we want to print what? We want to print also the validation loss, because the validation, so you guys see that the training loss and the validation loss have different information, right? The training loss basically means what? The model is learning from the training data, and then you're reporting the training loss. Well, it's going to be really good because that's the data it's using to learn. But when we use validation, it's different because it never looked at that data for training. You see that? So you train with train, but you never train with validation. So therefore, looking at validation loss is actually more important because it tells you more about how good the model is. So you want to definitely have that in there. So if you notice here, then I'm going to say validation, maybe out of space, probably. Validation loss, val loss dot item, and then here dot for F as well, just a formatting, and close the double quotes. So I think that shouldn't have any errors. All right, and that's basically, I think we're done actually. Yeah, so if there are no errors, we should be able to run this. So let's try it. Error. Okay. Yeah, I should only have one colon here. All right, see that? And there it is. So it ran, and we're printing both the training and the validation loss. At the end, we print out, what are these? What are those two values right there? They're the huh? What? Yes, exactly. The slope and the y-intercept, right? So they're basically the W and the bias of the equation. All right, that's very useful because I want you guys to just take like 5 to 10, five temperatures, right, of Fahrenheit. Use this to calculate Celsius and convince yourselves that it works. Right? Do that for a few minutes. I'll be right back. Did you guys try it? Those parameters to calculate between Fahrenheit and Celsius? Anyone? No? Okay. Well, huh? You're still what? Okay. All right. So anyway, that should be the point of this exercise is to show you that these parameters are actually very useful, right? They're very useful because they allow you to, to figure out the equation that does the calculation. So if I do, I'm actually going to Google so Celsius to Fahrenheit, I think, or Fahrenheit to Celsius. Equation is what is it? Now, it may not be exact, but what is it? So it's something like Fahrenheit minus 32 times 5 nines, right? That's probably what you guys found. So yeah. So in our example, it is basically the x, right, times 5.37 minus 17. So let me grab my calculator. What's one Fahrenheit temperature would be, let's say 75, right? So 75 times 5.37 minus, okay, maybe that doesn't work. Could it be the other way around? Is it Celsius to Fahrenheit? So what is the Celsius temperature? 0 is 32, right? So 0 is 32. I don't know how accurate this is. It may not be super accurate, but the idea would be this. Yeah, so 38 is 100. So it's gotta be actually Celsius to Fahrenheit. I think it is. So Celsius is 38 times 5. 38 times 5.3 minus 17. So it gives me 184. It's actually 100 degrees. So it's not perfect, but given the, so this is actually a good question. What would make these values better? How could we get better values? Huh? More iterations, that's a good one. Also, just more data. Just more data, right? We really train only on 7 pieces of data. If we had way more, we'd probably get these to be better values. But at least what's important here is, what I want you to understand is that those parameters actually have some important implications, okay? The other thing I want to show you is the loss. If you look, the loss here implies that this is the error that you were getting at the beginning. 85 for the train set, 56 for the test set. Do you see that, guys? Now, keep in mind, your test set only has 2 samples, right? So it's not really that great. But what pattern or trend do you notice in both the training loss and the validation loss? What do you notice there? Huh? Well, it's just going down, right? So we don't have to maybe look at exactly what the pattern is, but we definitely can notice that it's going down. All right, and that's what we want. We want the loss, as the model is learning, is getting better. So over time, as the iterations are advancing, the model is better, which means the loss function, the loss value is going down. And that's exactly what we want. You guys see that? Does this make sense? Now notice we didn't provide any accuracies or anything like that in this problem. That's something that we will look at in the future. But certainly at this point, what we can see is that the model is doing really well. Okay, so that's basically our example here. Any questions? No questions? All right. So as homework for next week, what I'm going to ask you to do is basically use this exact same model, but use real data. All right, so create data. Create data that is, so that we can improve these results. So you'll have to figure, obviously, I don't recommend that you hard code the values. So you're going to have to read them from some kind of a text file. So go online, right? Go online and find some data of Celsius to Fahrenheit, right? Or really, does it have to be Celsius to Fahrenheit? It doesn't, right? Why? Because we're not building a model for Celsius to Fahrenheit. You guys get that point, right? Nowhere in this are we saying, oh, the laws of physics say this and that. We're saying here's some data, right? The inputs, and here's some data, the outputs. Predict. So really, it doesn't even have to be temperature, but what I do want you to do is to find some data. It's large, considerably large, 10,000 or so. Obviously, it'll come from a text file. Load it. You know how to load things from last week, and then do this exact same exercise with that data. Does that make sense, guys? So I'm going to create the Dropbox for this. Okay, so I'm going to go ahead and go to Brightspace. And then we'll talk a little bit about the homework in the time that we have left. So before I finish with this, so I'll actually stop the video in a second. But are there any questions about what we did today? Guys, any questions? It all made sense? All right, great. So keep in mind what we're going to do next Monday is similar, but now we're going to look at not linear regression anymore. We're going to look at, classification. So we're going to basically look at the, building models. It'll be the same type of template, and we're going to actually, so you should be excited because we're going to actually build a neural net. All right, and you'll see this actually, not that complex. A lot of, the way that I like to put it is in terms of building the pipeline for a deep neural net or a neural net, you're already 60% there with this. You see, and now we just have to focus on a few parts, right? So as you might imagine, the parts that we have to focus on are these two, really. The model itself, that's why we always want to keep it separate, right? We always have it as a separate thing because that way it allows us to independently change that, what is called the architecture, and of course the loss function, because they have to be specific to the type of problem we're attacking. But a lot of the rest of the code is going to be pretty consistent. Okay. All right. So I'm not hearing any questions. So I'm going to stop the recording at this time, and I'm just going to focus on setting up the Brightspace new link for the homework, second homework. Pretty easy homework, I think. And then, if you have any questions about the assignment, you have an assignment due tonight, correct? Yeah. All right. So I'm going to go ahead and just close this one.